like all the presentations today and tomorrow, I could fill several semesters worth of material, and I'm just trying to compress everything down to half an hour. So I picked two themes, that the 2 points I want to get across, and everything else is just gloss on those two points, and I'll give a little test at the end to see if I succeeded or not in getting those two themes across. So first of all, I'm not really going to talk much about the software part. It's hard to give talks where you really focus on the software and how to do things and so forth, but I do want to say a little bit, because in the end, when you're using algebraic solvers, you really should be using libraries. You shouldn't be writing it yourself. And so I just really wanted to say something very briefly about these pieces. From the aspect of my presentation, I've listed that PETSI and sundials really kind of fit the paradigms that I'm going to talk about and how I think they're natural and easy to use. Trilinos is a bit older. It's a lot of stuff put together. It's not so easy to do things. Julia Julia, I don't really know much about. Haven't used the toolkits for linear algebra and PDEs and so forth. Python SciPy is kind of in the middle. It really needs a lot more maturing, I would say, over time to get up to the kind of natural usability that I'm going to talk about with PETSI and sundials. Okay, so the first little part is, where are these equations coming from? I'm not talking about linear algebra in general. I'm talking a subclass of linear algebra for problems that arise from continuum problems. So Robert talked a good amount about BLAs, which are working with dense matrices, which are appropriate for a certain class of problems. Generally, for continuum problems where you're starting with a PDE, dense operations are generally not the most appropriate. And we'll see why in a minute. So we're starting from this kind of vague abstract idea of we have some PDE, which depends on time and space, and some kind of boundary conditions, which I'm never going to talk about. And now we're going to go from that PDE to a discrete representation. So first I pick a model, the heat equation, very simple, parabolic PDE. And now I do a very simple discretization. So I'm simply replacing the derivative in time with a forward difference, and then a derivative second derivative in space with a center difference. And we see that if you just do Taylor series expansion on them, you get some order delta t and delta x squared in there, which tells you how close one could hope this would be to the continuum problem as you refine in time and in space. And for kind of classical discretization techniques, classical finite difference and finite element, generally these are relatively low order. So you might have delta x to the fourth, and you might have delta t going up to 2 or 4 or so forth, but not more than that. Spectral methods are a great way to crank up those numbers, so you can really get those very small. But in the more classical technique where you're using traditional finite elements, finite differences, those O's can be fairly large. And that's why the problems become big. In order to have an accurate solution, we got to really force this guy and this guy to be very small relative to this term, which means we have to have a very big n. That is the dimension in x or x, y, z, and so forth. So that's why we're talking about big problems. And when I say big, an n of 1,000,000, n is not this n here, by the way. It's the size and dimension in space, is small. And for real serious problems, people go up to the billions and even hundreds of billions. Very large problems. So anyways, this discretization, which uses the forward difference in time, centered in space at the previous time, gives you a nice little formula for the next solution from the previous solution. There's another approach, which is to do what's called implicit in time. So rather than discretizing the derivatives of x with respect to x at the previous time step, we discretize them at the new time step. We don't know them yet, of course. Now we can move those unknown u's over to the left side, and we end up with an algebraic equation for u n plus 1. And so these correspond to the two basic approaches that one works with when you have PDEs with time. Implicit, like this, or explicit, where you don't have to solve algebraic equations. Now, solving algebraic equations, of course, is much, much more expensive than simply applying the operator as here. So why would one ever do that? Well, that goes beyond the topic of this talk. It's related to the stiffness of the problem. For many problems, they're what's called stiff. You have to use implicit methods. So you don't have to worry about that today, but they would talk about it in any ODE class. Okay, so now going back to my first general principle I want you to think about with relation to algebraic solvers for PDEs is that from our PDE, I've shown how we can move to a linear algebra setting, which may involve linear solves or nonlinear solves. Same thing holds if your PDE has nonlinear terms in it, then it's just kind of, you get nonlinear algebraic equations. And the thing that is important is that the structure and properties of the PDE that arrive from the differential operators in the PDE become structure and properties of your linear algebra. And the key to getting good performance, that is actually being able to solve things in a reasonable time, is you know the structures arising from the PDE, thus you know them in the linear algebra, and then you take advantage of them in the linear algebra to have more or less specific algorithms that take advantage of those things. So the first structure, which was clear from the previous slides, is the non-zero structure of the linear algebra. The nonlinear structure of the matrices just arises from the fact that differential operators are local, because you're just looking at local values with derivatives. And so naturally, with traditional finite difference, finite element discretizations, your matrices are very, very sparse, and they have a lot of locality. And of course, we're going to take advantage of that, because if everything was dense, we'd be trying to use BLAS and LA-PAC on a billion unknowns, which just doesn't make any sense at all. Then there's more specific mathematical properties, like if you start with a uniform elliptic PDE and discretize, you end up with positive definite matrices. Positive definite matrices are great because they have a lot of additional structure, and you can use, for example, a conjugate gradient method to solve with it instead of much more expensive methods like GMRes. Things like when you can do a Fourier series expansion for PDE solutions, that corresponds to just linear algebra expansions, and you have similar orthogonality properties that you had in the underlying PDE. So Robert talked a bit about discrete Fourier transforms and so forth. That's where this fits in here, and that's why you can use FFTs to solve many PDEs really efficiently, because you're taking advantage of this structure that comes from the underlying PDE and appears in the linear algebra. More generally, the whole structure of the differential operators impacts the structure of the matrices, sometimes in a clear way, often in an unclear way, and you want to take advantage of that whenever possible. So, for example, this kind of fits in the world of why does multigrid work? It doesn't work for a random matrix, but it works because the matrix comes from an underlying PDE where there's structure in the solution space that you take advantage of in linear algebra. So algebraic solvers always take advantage of these inherent properties that they inherit from the PDE. So now I'm going to jump a little bit to what I call the algorithm stack. And the algorithm stack for algebraic solvers per PDEs really has three basic levels: the time integrator level, then the nonlinear solver level, the linear solver level, and then underneath that is basic linear algebra vectors and matrices. This vectors often corresponds to BLAS level 1 stuff that Robert talked about. The matrix operations are generally sparse, and so they don't directly utilize the BLAS and LA-PAC, but often inside, for example, factorization, you're doing a sparse factorization, you end up with some block structure, so you're still actually ending up using BLAS and LA-PAC inside a lot of the pieces along here, but it's not the only building block, it's just one of many. And I already introduced this idea of explicit and explicit formulations for solving ODEs. There's a combination form called implicit-explicit. There's also tricks you can play where you just make, where you just kind of related to that, where you have a linear implicit part, so you only have to solve a linear system at each time step instead of nonlinear systems. And I've just kind of organized this. And the reason I'm putting this up is 25 years ago, I didn't put up this slide. 25 years ago, the top it said the software stack instead of the algorithm stack. But I've realized that the key is actually all of these things are algorithms, and it's really an algorithm stack, and corresponding with that is a software stack. And a good software stack to solve problems that are related to this looks exactly the same as this. So understanding the algorithm stack tells you what the software stack should look like. And once you understand this, it's almost often should be a trivial translation to the software stack. And I just want to dive in on one little piece, just diving in on the preconditioners from here. I noticed that inside there's another layer of lots of things. And many people's careers are just on, say, this piece or that piece and so forth. And this is true for every block in the algorithm stack. And of course, to solve problems in simulation, no one can know all the pieces, but you have to know enough about the pieces and how they fit together. And then when you need to dive in and get expert help and say, oh, I have to use algebraic multigrid, I'll get some expert help there. But in the other parts, I don't need expert help because I have enough underlying understanding of the algorithm stack. Okay, so the second theme, or maybe it's a third, is this idea that algebraic solvers for PDEs are really compositions of simpler solvers for simpler problems. You combine those together to solve a complicated problem. You never have a really complicated problem that have some hugely complicated algorithm to solve it, where that hugely complicated algorithm is not actually the combination of a bunch of simpler algorithms. That would just be monstrous. How could anybody ever do anything? How could you ever analyze it? How could you ever implement it, and so forth? So as I mentioned before, the key point is the software stack should mirror the algorithm stack as much as possible. So let me go a little bit detail of this for just a couple of things. The idea of the composition is, say I have it's actually not even written as a PDE here, but I've already gotten rid of the PDE part. So I have ODE, where I have a stiff part and a non-stiff part. And say the G is expensive to compute, and its Jacobian may be quite a monster. So I don't want to need the Jacobian to do the calculation. But the A is stiff, and so I require an implicit part for that. So IMEC methods combine the two. So we're combining an implicit and an explicit step together. The algorithms are actually a bit more complicated than I've written here, but conceptually you can just think that we're using the new time step U in the implicit part with the A and the old time step in the G. So the solve part will only involve a solve with the matrix A. So I'm just looking at a problem in 2D with a grid like this, and I have this kind of setup. So how would one want to write this in a composed way in software? So in PETSI, you would write it in the following way. You would just provide 3 functions, or if you want to think in a Python world, maybe 3 objects, however you want to organize it. But you provide an implicit function that defines the implicit part of the equation, and you need its Jacobian because you're going to use Newton's method on it. So you provide a way to get the access to that Jacobian. But for the G part, you only need to provide a function. You don't need to provide the Jacobian information if you're just interested in solving it. So in PETSI, you would call these 3 functions, and then to select the solve process we want to use is very simple. You can do it in code, or you can just do it in this kind of format that we have. Could also be JSON. I want to use an implicit RK method, which is actually an IMEC version of an implicit RK, so it takes both of them. And I'm going to solve the A, I'm assuming is related to diffusion. So I have two fields in the A, U and V, so it's kind of confusing there. Sorry about that. And on each one of them, I want to use algebraic multigrid. So I use a preconditioner that consists of two parts, one for each of the two variables, and each one just diffuses with weak coupling between the two. So I can just use algebraic multigrid on each of the diffusion problems as my preconditioner, and then it's accelerated with GMRes, normally something else down there. So I've composed the two parts together, and I've also decomposed the stiff part into two parts, and I solve each part of those. And I don't have to write a lot of complicated code for this.
Sorry.
Yep, go ahead.
What type of code is the bottom box? I don't
Sorry,
understand.
This part, this.
No, what is that?
So we have we call it the options database, but basically it's a set of options that you provide. I've just formatted it kind of nicely, but it's basically just, in a simplest form, just command line options. Oh, so it's just a list of keywords and values, okay. Keyword value, keyword value. Okay. It conceptually is nested. That's why I've written it inside, that this subpart applies to the PC.
It's a bunch of command line options. Okay.
Yeah, but in a JSON file, you can make it in a nice nested way.
Okay, and the Jacobian means the A matrix.
The Jacobian in this case is exactly the A matrix.
The nonlinear function is G.
Yep.
And there's no right-hand side here, because there's no driving.
No, the right-hand side is the G in this case.
G is the right-hand side.
Yeah, okay. We just call this right-hand side function because I called it that 30 years ago. It should really be like an E function for explicit part. And much later, another person decided to call this I function, and then we had this disconnect between the two. This should really be called the E function for explicit part.
And TS stands for time step?
Yep.
Okay, so,
and that's just the guy that manages the time stepping. Okay, now I'm going to actually look at a slightly more realistic problem, which is very similar to this, is we make this a reaction diffusion equation. So we have two terms again, like before. I've just put a scaling in front of A for no reason at all. But in a reaction diffusion equation, both the diffusion is stiff and the reaction is stiff. So you can't use just an IMEC method on it. You actually have to solve a system related to the entire problem. And if you just look at this and you apply the new n for the G term, then a Newton step looks something like this. So for each Newton step, you have to solve with this A, and then shifted by also the Jacobian of the G. Okay, and now what we're going to do works really, really nicely is the diffusion, again, we're going to solve with multiple independent diffusions for each of the components. And for the reaction, but all these models, basically what you think of it is there's a little reaction happening in each cell, and then there's diffusion between the cells, and then there's a little reaction in each cell over and over again. But the reaction term, which may have many variables and be rather complex, is also stiff in itself. So you can't just do an explicit step on that. So how are we going to do that? Well, much like the previous page, we're going to apply a preconditioner, but now the preconditioner has to involve this part here. So let's go to the next to clarify this. So going back to Alex's question, now we have to set the Jacobian for the G term. So you just call this one extra thing and say, now I'm providing the Jacobian for the G term, and I need to have my RK method actually now be fully implicit. So I just turn this flag on to say both terms should be treated implicitly. And now what happens is the entire right-hand side, which previously was treated in two different ways, all becomes one nonlinear system that has to be solved and is solved with Newton. And I'm going to use for a preconditioner a composite, so a combination of things. And the combination are the things are, the two parts are this field split and then a point block Jacobi, where point block Jacobi means on each cell it solves with basically actually with LU, even though I don't say it here. It solves each of those little guys with LU. They're small. It's okay to have a whole bunch of little LUs. And then again, of course, these two fields, or whatever number of fields there are each solved independently with diffusion. Now, in general, for reaction diffusion problems, not all the components really diffuse, only a few diffuse. So you'd have a small number of these, even though you have many components in the system. You don't have to worry about the diffusion of all the other terms. Okay, so there's this great book that's actually written by the advisor of one of my postdocs, so we have a very interesting relationship that I think is a really fantastic introduction to how I think about these things. Even though he wrote it, it's completely his work, where he tries to introduce numerical solution of PDEs in this context of where the algorithm stack maps back to the PDEs you're working on and maps forward to the software stack. So if you're interested in this topic, I think I really recommend taking a look at this book. It's relatively elementary, fairly easy to read. So just a summary. As any of you who's worked with solving real PDEs on real problems, it's a lot of work. You know, you don't just do it in a day. It's a big project. But if you understand your model and its decomposition, it becomes easier to build up a solution process. And you really have to understand how the algorithm stack fits together. Once you understand the algorithm stack, the software stack is pretty easy. And you should use a library, which are the more modern libraries are becoming more like this, where the software stack really mirrors the algorithm stack. So it's almost a mapping between the two, as opposed to trying to figure out this really obscure library that doesn't seem to have much to do with directly with the problems you're working on. So I'll take any questions. Yeah.
So whenever I see something like this, it's very daunting coming in from the outside. Yes. Is there any kind of tools, or are people working on research to do some of this automatically? Or is this all still you learn the algorithm stack, find a friend?
There has been work for quite a while, I would say. I know personally not collaborators of mine, but collaborators of collaborators of mine, going back to at least 2010, trying to use kind of older ideas from AI as to how to organize things and kind of figure out automatically. The problem is really, I would say, that we don't have yet a good representation of the mathematics of the problem that you could feed into the tool that would then tell you which approach you should use. Because if you wait and say, generate this gigantic matrix and then feed it into a tool that's supposed to figure out which approach to use, it doesn't make any sense. It's lost all that information. So you really have to have a tool where you can somehow represent the properties of the differential operators you're working with, and which are small and compact. It's just a few letters and you're done. And map those over to the logic of the algorithm stack. And I don't know how to do that. It certainly should be possible in the long run, and I think that's the approach that's doable, but the kind of go to the matrix and then try to figure it out just doesn't work. And that's most of the work that I know about.
So I know very little, nothing about this subject, but basically the calculations tend to happen in cells, right? And these cells tend to be cubes or squares.
Well, there's really two formulations. One that uses structured grids and then one that uses unstructured grids. And my example is just with structured grids because it's so much simpler. The ones with unstructured grid where the cells arbitrary shapes or tetrahedra and so forth and packed together in different ways. A lot is the same because you still have the locality, so you still have the same kind of local non-zero structure, and you still have the PDE properties that come through. The difference is that the matrices don't have kind of the trivial non-zero structure that you have when you have a uniform, nice uniform grid, where it's like a diagonal and then several others. Instead, it looks complicated, but it's just nearest neighbor, or nearest neighbor, neighbor, and so forth.
Okay, my question is, in the uniform case,
Yep.
I did some experimentation with reaction diffusion, just for my own amusement, basically. But the results coming out look suspiciously aligned with the cubes and the diagonals and things.
Yes,
How
that can
do-
happen, absolutely.
How do you make that so that the boundaries of the cubes don't actually exist in a real
Yeah.
system, right? So how do you make that
Well, if you're,
those artifacts not happen?
I would say if you're just doing a pure reaction diffusion, I'd be surprised if you saw much of that. But if you have any kind of convection or flow type stuff, then you'll definitely see it. And there's a whole universe to work on that. I mean, Alex knows a bit about it. Marcia Berger knows a hell of a lot about it and so forth. That's not really what I work on that much, but it is an issue that is known and dealt with in various ways. Yeah.
What are those waves called?
Sounds like you're
Yeah.
not solving it accurately.
Well, yeah,
But-
I had a really stupid
You need to
implementation.
refine your grid more.
Well, yeah, but
But
sometimes
refining
just,
the grid just makes
yeah,
the
sometimes
I mean, that
just
doesn't really
refining
address
a
the
grid
problem.
doesn't resolve these kinds of issues.
Yeah.
Yeah. It depends what the source of error is. If it's
Yeah.
the order x squared term in Gary's first slide, or if it's the order delta t term, so you have to assess convergence and see where you're at.
Okay, I guess. And the next question is, how do you assess convergence? when-
Right. So you
So,
one way to do it is to refine the grid and see how far is the new solution from your previous one. Plot these things, you'll see a slope, and then decide where you want to cut off that slope and say, okay, I'm okay with 10 to the minus 2 accuracy, and in this measure of my accuracy, I'm at 10 to the minus 3. So I'm
all right, thank you.
Any other questions, or we break? Let's break.